Good morning, everyone. So today I'm going to talk about physics as inverse graphics, work on artificial intelligence from the University of Edinburgh. This paper was put on the arXiv May 2019, and will be presented in an artificial intelligence conference this year, the ICLR. So before talking about inverse graphics, I'm going to talk about graphics. In this context, graphics is you want to produce an image or a set of images for a video, for example. And graphics, you take physical properties of the things.
Desculpa te interromper. Talvez tu consiga deixar em tela cheia a apresentação. Não sei se tem como...
Não está em tela cheia?
Não tá. Aqui tá como...
Eu acho F5. Aperta F5.
Deixa eu ver aqui.
Às vezes, de repente, às vezes ele abre duas janelas e tu tem que compartilhar aquela que está em tela cheia. Aí, perfeito.
Aí.
Vai.
So, in graphics, you take physical properties from a system, for example, mass, gravity, spring constant, whatever physical system you want to simulate, and put these physical properties on a physics engine. A physics engine is what takes these physical properties to simulate the environment or the physical system you want. For example, like physics engines, Blender, Unreal Engine, Unity. So the example here is an image that's produced by this physics engine that takes as an input these physical properties. In this case, it's an image for ray tracing that produces reflection and this kind of things from optics. So the idea is, can we reverse this process? We take the image or a video, pass through a physics engine, and obtain the physical properties of this image. Well, this is one question. The second question is, why do you want to do this? So, for example, a system where reverse graphics is very useful is self-driving cars. In self-driving cars, you can use cameras, but the self-driving car has to know the position and velocities, for example, from the other cars, from people, from all the objects from the environment. So you want to take this video, the images from a video that has on the self-driving car, and you want the self-driving car to estimate these physical properties so we can plan how to best drive. Another example where reverse graphics is useful is simulation of real environments. For example, here you have the first image, a real system, which is a ball falling through a fluid, and the second one is a fluid, I think it's honey, pouring through the paper here, and you want to simulate this in a virtual environment. To do this, you have to obtain the physical properties of the system to put it through a physics engine. So you need to somehow obtain these physical properties from the images. Well, how can we do this? Through artificial intelligence, because we don't know exactly how to obtain these properties from an image. You let an artificial intelligence learn how to obtain these physical properties. This artificial intelligence is on this slide. There's a lot going on here, but there are 4 components. The encoder, which is the bottom here. The encoder takes the image and pass through the second component, which is a velocity estimator. The velocity estimator takes this component and pass through a physics engine. And the physics engine passes to the last 4th component, which is a decoder. I'll explain each one. The encoder is the first step. The encoder takes an image, passes through a neural network, and outputs the positions of the objects in the image. A neural network is a very simply, it's a function approximator. Neural networks have 3 parameters that are adjusted by optimizing a objective function, a cost function. So this is what the encoder does. You take the image and outputs the position of the objects in the image. So this is the first step here. The second step is you take the position of these objects in the image and estimate the velocity. But you only can estimate the velocity with more than one image. If you have only one image, you can't obtain the velocity because you need the difference between 2 positions. So what you pass is 2 or more images through the same encoder, and through these encoders, you estimate the velocity. This velocity is also a neural network. So the velocity estimator takes these positions here and output the velocity of each object in the image. Now, the velocity estimator passes the velocity of each object, and the encoder passes the position of each object to the physics engine. The physics engine is the set of equations from which the physical system you want to simulate. So here in this paper, they use 2 balls and on a spring, 3 balls gravity, 3 balls influence each other by the gravity, and a pendulum. So the physics engine has these equations from each system, physical system. This physics engine has the physical properties of the system, which from the first you don't know these physical properties. They are estimated by the neural network. So for example, the 3 balls gravity estimated the gravity force from the encoder and the velocity estimate. The last part is the bit hard. It's the decoder.
2 minutes.
Yes? Okay. The decoder does a lot of things, but what the decoder does is the graphics part. So up until the physics engine, it does the reverse graphics. You get the image from the physical prop. You get physical properties from the image. Now, the decoder produces the image from these physical properties, and it's trained end-to-end. These output images here is what allows the neural network to train by an unsupervised manner. So you don't need labels, or you don't need to tell the neural network what to do to train it. So there is this loss function, which is the object function you optimize to train this neural network, which is the difference between the predicted image and the actual image. So this is the results. The bottom row shows the true sequence of the simulation, it's the 3 ball gravity, and the first row shows the prediction from the neural network. As you can see, it's a good prediction because the first and second row is very similar. This is the spring. It's 2 objects, the 0 and 5, connected by the spring, same way. The bottom shows the true sequence, and the first row the model prediction from the neural network. Also, you can use to simulate a physical environments for predictive control. For example, you want to control this pendulum to be upside down, the reverse pendulum, and by make predictions from the physical properties, you can accelerate the way the neural network can make this physical system behaves. So conclusions, we can do inverse graphics with machine learning, and so you can obtain whatever physical properties you want from whatever physical system you are simulating. And inverse graphs allow for predictive control, which is useful for robotics, is useful for games, is useful for self-driving cars, and so on. Thank you.
Thank you, Thiago. Muito obrigado. Tempo perfeito, hein?
Thank you very much. Very interesting talk.
Yeah,
Thank you.
Very interesting indeed.
Oi, legal pra caramba.
Então, nós podemos passar para perguntas, e perguntas podem ser em inglês ou português, fiquem à vontade aí.